All right, I'd like to look now at the timer. We're going to introduce a few new concepts here with the timers. Let's start with timer.h and see what kind of functions we'd like to put in here. I'd like to create, like we did with the LED, a timer init. I'd like to also create a timer get function that returns a timer value and a timer set function. I'll make this one a void. Timer set. The reason I'm leaving the type off is I want to talk real quick about how big do we want our timer to be. If we make it a small number, like a uint 8, it can only hold up to 256 or 255, right? 0 to 255. I want to create a millisecond timer in here. It's going to count milliseconds for the system. If I do a 32-bit timer, then I'm looking at 4 gigaseconds, which is quite a long time, but it's still like a month or two, I think, if I did the math right. But if I use a 64-bit timer and I count milliseconds, that will last longer than I'll be alive by quite a bit. So I'm going to go ahead and go that way for now. Now it makes it bigger. It makes our math on it bigger as well. There's a penalty with it. But since it's a pretty simple function, I'm going to go in here and use this for now. And that way I don't have to worry about the timer ever overflowing. I can just assume that it has been has been working the whole time. The problem when it overflows, if you're doing subtractions on a timer, if the new time is you want to see how much greater than the old time it is. Well, if it has flipped and now the new time is less than the old time, you have to count for those situations, and that can be some tricky code and just a hassle. So I want to avoid that. I'm going to use the uint64 for my timer. So these are the 3 functions I want: timer init, timer get, timer set. And that's it for my .h. Let's go to the timer C, and I'll drop these in here, just as we've done in the past. And we'll put our functions on them. Okay, and there's our timer. Let's look now at the timer init. I'm going to paste this in and then talk about it. This timer init is ugly. As you can look at it here, it's straight out of the data sheet. Here's kind of the comments of what we're doing. I'm using timer counter 2 for the rotary LEDs because, as you recall, we're using timer 0 and timer 1 for the PWMs on the LEDs. So I'm going to use timer counter 2 for this one. I'm going to pick a clock value of 250 kilohertz and set that value in OCR2A as a top to be F9, and that'll give me 1 millisecond. All right, the rest of this is just setting up registers. If you want to know what this means here, I'm going to see if this works. If I go to the implementation, no, it's horrifying. I'll have to go look at WGM21. We're going to go to our dependency file, look at our IO328, and find that. So in TCCR2A, that's the register we're setting. These are the bits. WGM20 is at bit 0, WGM21 is at bit 1, and these must be bits at 4, 5, 6, and 7. So going back to the timer, I want to take a 1 and put it in the WGM21 bit. Well, WGM21 is defined as 1. So this is a 1 left shift 1, so it's going to put a 1 in that bit, put a 0 in bit 20. Yeah, that's the nomenclature. Take each of these and OR them together, and that will give you the value you need to fill in TCCR2A. Same thing here for TCCR2B. All right. At the end, we have to make sure we turn our timer mask on, and here I'm turning on OCIE2A. I will leave it for you to go through the data sheet and validate that this will in fact give you a millisecond timer with the interrupt enabled. But it does. Now the question is, when we have the interrupt enabled, where is it going to go? Well, we're going to need to go down to our ISR and create an interrupt service routine for it. The way that is done in Atmel Studio, or in AVR GCC, the compiler, is to use the keyword ISR. This is not a C function per se. This is something built onto the compiler. It will compile this like a normal subroutine, but it will then place it in the program memory and then place the appropriate interrupt vector jump in the interrupt vector table for you. So we just need to know which interrupt vector is it. And right now it doesn't know. If I type, oh, it does. Why does it know that? It shouldn't know that yet. Normally, well, I'm going to try this. We'll see what happens. This is timer 2, compare vector. And we're timer 2, compare A vector. That's the interrupt we're using. What I'm expecting I would have to do is come up here and pound include AVR interrupt.h. If we were to go and look at the AVR GCC live, and again, online user manual, library reference, AVR interrupt.h. Here's the instructions for how to do the ISR, and then the list of all the ISRs is down here for all the different chips. That'll give you the names you need. But again, it's an Atmel Studio. Sometimes you can just guess and figure them out from just punching the right numbers. But that's the actual vectors. All right. So what do I want to do in here? Well, I want to increment a millisecond timer. So I'm going to call it millis. Now, if I were to make this a UN64_T millis and define the variable, this would be a local variable. And every time I would come in here, it would be different. So it would be undefined right here. So that won't work for us. We have to actually declare this as a static. When you declare a variable as a static in C, it will save the value on every call. What that means is instead of a local variable, I'm going to do a local here again, int A. When I declare int A, it gets pushed onto the stack. That's where local variables are created. Just like the parameters that are passed to a function are put on the stack, a local variable would be created on the stack. And so when that local routine exits, the stack point is reduced, and whatever's on the stack is considered garbage. So it is gone every time you call the routine. However, when you declare something static, it is not put on the stack. It's put into the global memory system, what they call the heap. But in this case, you can think of it just as a section in your data memory. So it's allocated there, and it's not cleared. It's actually reserved. Every time you call this ISR at this point, millis will actually increment over what it was the time before, which is exactly what we want. Statics, you might want to say this, and it wouldn't hurt to say this, but all statics in C will default to 0. The C system will take any variable that's on the heap or in the global memory and will clear it to 0 if it's not initialized to something else. Okay, now this is all well and good, except because it's static, it's only available inside of this function. No one else can see it inside the rest of the file. So if I want to use millis anywhere to see it, I've got to be able to declare it outside. So I have to take this away and make it a global variable. So I'm coming all the way here to the top, where I will declare it here. Now this causes a slight problem. We talked about this in class, and it's a very important concept. Millis is being changed inside of an ISR. when any other function is looking, if this timer get or timer set is looking at millis, it will assume that it hasn't changed since the last time it got millis. So if something's changed in ISR, we have to declare it volatile. Okay, it's very important. Anything changed in ISR needs to be declared volatile. That tells the compiler, look, I don't care when you read it last. Every time you reference this variable, go get it from memory. Don't go get it from memory, put it in a register, and just use that register from there on out. Go get it from memory every single time you access it. So now we've declared our millis. We've set up a routine to initialize. We've declared the global variable millis. And every time the interrupt timer goes off, millis will increment. We're not concerned about overflowing because we have a 64-bit millis variable. Okay. Well, that makes our get timer fairly easy. What's in get timer? We're just going to return millis. Okay. And so it grabs the value that's there. So this way, if it wasn't volatile, it might go get millis from memory the first time, but then it knows from there on out that it's in a register, and it might just keep returning that value. So we can't do that. All right, what about the timer set? Well, I want to set my millis equal to the new millis that was passed in. That part's pretty easy. But now I've got a bit of a conundrum. I got to think about this for a minute. I'm going to do an 8-byte set here. And if you think about your assembly code, you need to recognize, well, that's not going to happen in one clock cycle. It's going to take a little time to do that operation, at least 8, we know. Probably more with all the loads and stores you're going to have to do. Okay? So what would happen if I was in the middle of copying millis, new millis to millis, and an interrupt went off? Well, I would come down here and I would increment this by 1 and store it back, and then come back to where I was, and I'm in the middle of a write here. Now, it's just one instruction in C, but you know now that it's more than one instruction in the assembly code. So I have to do something to protect this. Now, we talked about doing this before in assembly code, and you did a CLI to turn off the interrupt and follow it with an SEI. And that's one way to do it, but there's more stuff going on with the state and other things of the status register. So there's a function for this, and include AVR atomic.h, if I'm not mistaken. No, that's not right. That's why it didn't auto-complete for me. It's util / there it is, util / atomic.h. And you can look that up on the AVR GCC page as well. But I'm going to come down in here and use this function to do the atomic. So I want to make an atomic block. That sounds pretty cool. And what this will do is take anything inside of this new block and make it atomic. It'll turn off the interrupts. It'll save. Here I'm saying restore state. That tells it to go ahead and save the state that it had and restore it after this operation is done, to make sure that our entire system works like it's supposed to work. Okay. So here's an example of a static, global, a volatile, and an ISR, okay, as well as a full initialization using all of your standard assembly code type registers, but this is how you would do it in C. So with this, you should be able to create an interrupt at your own timer interrupt, or later on, you can create interrupts for the ADCs, the PWMs, the SPI, whatever it is you're going to wind up writing interrupts for. Okay.